Okay, Assalamualaikum and very good day to everyone. Alright, so we continue on the fundamentals of thermodynamics, part 2. Uh, the topic is on first law of thermodynamics. So, part 2 of 4 parts. Okay, so before this, we have discussed on the basic, what is the condition of each state. So here we proceed with the moving boundary work. So moving boundary works is one form of mechanical works frequently encountered in practice, as it associates with the expansion or compression of gas in a piston cylinder device. Some is on the gas, some is on the liquid. So during this process, part of the boundary, which is the inner face of the piston, move back and forth, in or out, and therefore the expansion and compression work is called moving boundary work, or simply boundary work WB. So here is the figure. So in the dotted red line is the moving boundary. So either it can be increasing or decreasing. Okay, so in this section we analyze the moving boundary work for a quasi-equilibrium process, which is a process during which the system remains in equilibrium at all times. So we consider in equilibrium condition, it's not in transient condition. Then consider the gas enclosed in the piston cylinder device shown aside. Okay, if the piston is allowed to move a distance ds, this is your distance, in a quasi-equilibrium manner, the differential work done during this process is force exerted by pressure, so your force exerted pressure is PA, pressure times area. ds is your distance, so we got area times your distance, we got volume. Okay, so the total boundary work done during the entire process as the piston move from state 1 to state 2 is integration of pressure d volume dV. So we got unit kilojoule. So consider the expansion process shown in a PV diagram aside. So this is only a element. This is your dA, the area element. Okay, so the total area A under the process curve 1, 2 obtained by adding this differential area, your area 1 to 2, 1 to 2 process, we need to integrate state 1 to state 2 in the area below the graph is equal to pressure times your volume, difference in volume. So compare with the previous equation, the area under the work curve on a PV diagram is equal in magnitude to the work done during an expansion or compression process of a closed system. I have discussed this in part 1. A gas can follow several different paths as it expands from state 1 to state 2. During actual expansion and compression process of gas in ideal process, pressure and volume of the process path often related by this here is a PV to the power of N is equal to C. C is your constant. or known as polytropic process, where n is a constant called as polytropic index, ranging between positive to negative infinite. We don't know the value unless we have determined it first. In general, each process path with different value of n will have a different area underneath. And since this area represents the magnitude of the work done will be different for each process, whereby it depends on the value of your n, power of n. So, types of moving boundary work. Boundary work occurs because the mass of the substance contained within the system boundary cause a force. So we got pressure times area. We have a force to act on the boundary surface and make it to move. This is what happens when substance in the figure, inside in the figure, contained in a piston cylinder device, expand against the piston and force the piston to move. Thus, boundary work is done by the substance on the piston. So, this substance will influence the movement of the piston. So, in this course, we are primarily concerned with boundary work due to compression or expansion of a system in a piston cylinder device as shown aside. So in all cases, we assume a perfect seal, which is no mass flow in or out of the system. So it's a closed system. No loss due to friction, so frictionless, and quasi-equilibrium process, in that for each increment movement of the piston, equilibrium conditions are maintained. Okay, so we have 5 types of boundary work as listed below. First is boundary work for constant volume, boundary work for constant pressure, boundary work for constant temperature, boundary work for adiabatic, and lastly boundary work for polytropic. So in general, the equation for boundary work, moving boundary work, is work boundary equal to integration of pressure times volume, change in volume. Okay, work for a constant volume process. It describes the behavior of substance inside the container that cannot be deformed. Since the volume remains constant, the heat transfer into or out of the system does not the pressure change in the volume works, but only change the internal energy, which is the temperature of the system. So this process called isochoric or isometric process, which means that the volume remain constant. The difference is normally in temperature. And sketch of the system and PV diagram process are shown in figure aside. So this is your figure. So PV diagram, your PV is your volume V is remain constant from area 1, process 1, initial to the final, constant. So since your dV is 0, volume does not change during the process, then the boundary works become 0 because your dV is 0. So pressure times 0, we got 0. So for ideal process, so basically your PV to the power of n equal to constant, then your n will be infinite. If we consider gas, since your mass, universal gas constant, and volume is constant, so the property relation of gas, we got something like this. See, we have moved out the mass universal gas constant, and volume. So, sample problem 3.2. Alright, sample problem 3.2. The pressure of the gas inside the aerosol can is 1.2 bar at a temperature of 25 degrees Celsius. Will the aerosol explode if it is heated to a temperature of 600 degrees Celsius? Assume that the aerosol can is unable to withstand pressure is excess of 3 bar. Okay, so this is the problem for work at constant volume. So basically, in this question, the total work is not being asked, but you just know what is the final condition of the gas. So 3.2. Sorry, 3.2. Alright. So given the pressure P 1.2 bar and the temperature P1. Temperature 1 is at 25 degrees Celsius. So given T2 is 600 degrees Celsius. Okay, so we assume it's an ideal gas. So PV MRT. Okay, so the condition is that your volume is constant. So P1 MRT1 is equal to P2 MRT2. Okay, so the mass also constant. The universal gas constant is constant because the same material. So we got P1 T1, P2 T2. Okay, so the question is to know what is your P2. So P2 is 1.2 bar per 25 degrees Celsius times 600 degrees Celsius. Celsius potong, and you got bar. So knowing that if the pressure, the final pressure P2 pressure is exceeding 3 bar, so the aerosol can is fail. Alright, so thank you. So work for constant pressure process. Before this, we have discussed on the constant volume. So at constant pressure, the heat transferred to the system does work and also change in internal energy of the system. So this called as isobaric, and a sketch of the system and the PV diagram of the process are shown in figure aside. Something like this. So PV diagram, constant pressure from initial to final state is a one straight line, one horizontal line. So since the P pressure is constant, the pressure does not change during the process, then the boundary work becomes, so we integrate from state 1 to state 2. So you got PO, P pressure remain constant, is only change in volume. Or you got a times mass. So here we got kilojoule here we got kilojoule per kg. So if we consider gas for ideal process, your N will be 0. Then for ideal gas, PV-MRT, as your MR is similar from initial condition to final condition, and your pressure also constant. So we got this equation lah for ideal gas. Sample problem 3.3. Okay, example problem 3.3. A frictionless piston cylinder device contains 4.5 kilos of water vapor at 0.4 megapascal and 200 degrees Celsius. So heat is now transferred to the steam until the temperature reach 250 degrees Celsius. If the piston is not attached to a shaft and its mass is constant, determine the work done by the steam during the process. Okay, so basically here, this is the constant pressure process. So basically, given directly the mass is 4.5 kilos, your pressure 0.4 MPa megapascal, sorry, big M, and the T1 is 200 degrees Celsius, and the T2 250 degrees Celsius. Okay, so work is constant pressure. So the work is from state 1 to state 2, pressure constant, so at dV. So rearrange solving this general equation, you got P V2 V1. Okay, so here we should know the properties here is water. It's not ideal gas. So ideal gas we use difference formula lah. So this is for water. Okay, so if for water, so we got pressure, we have V2 and V1. So basically here given is a mass, so this is the volume meter cube. Okay, so we should know the condition, the water condition here. Alright, so as it in the question given is in water vapor, so what types of vapor condition? So we need to check. Okay, firstly you need to go to your steam table. Okay, as we refer to saturated water pressure table, table A5 at 400 kPa. So the saturated temperature is 147.9 degrees Celsius. So given here is 200. So it's not in saturated water. So it's in the superheated. So superheated, table A6. So we got 0.4 MPa. So we have 200 degrees Celsius. So determine your V1. Okay, so V1 is in meter cube per kg. Also at 0.4 MPa at 250 degrees Celsius. V2 directly from the tables, meter cube per kg. Okay, so substitute into your general equation. So your work P V2 over V1. So you got, this is MPa if you use MPa. So MPa times, you use here, okay, so work is PA times area, it's not volume, so you need to times your kg. So kg here is 4.5, so you can take out the kilos. So you got Newton meter, your work. Okay, thank you. Sample problem 3.4. So this sample problem you can do by yourself. Okay, so work for constant temperature process. So for constant temperature, we also call it as a isothermal. And a sketch of the system and the PV diagram of the process are shown in the figure aside. So this is your figure. The PV diagram, something like this. This is isothermal from initial to a final. If we have a reversible, so this is your initial, number 2 is your initial, number 1 is your final. That we call it as a reversible process. For ideal gas, your temperature is equal to constant, then your PV MRT is equal to P equivalent to C constant divided by volume. Then the boundary work becomes something like this. So you can integrate volume. So you got ln V2 divided by V1. Or also we have P1. If you don't know the value of C, the constant value, so we can also use pressure 1, volume 1, ln volume 2 divided by volume 1. If we have the temperature and the universal gas constant and the mass, we can use this equation for work. For ideal gas, state 1 to state 2, PVMRT as your mass, universal gas constant, and temperature is constant. So take out, you got this equation. And the work is similar with this equation. Sample problem 3.5. Okay, sample problem 3.5. A piston cylinder device initially contains 0.4 meter cube of air at 100 kPa and the temperature is 80 degrees Celsius. The air is now compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. Determine the work done during this process. Okay, so 3.5. Okay, so given directly the volume 1. is 0.4 meter cube, and your pressure P1 is 100 kPa, and T1 is 80 degrees C. So the air is compressed to V2 0.1 meter cube. Okay, so basically in this exercise the temperature remain constant. So we got the work is total 1/2 dV, and also is remain constant. We have in the exercise, so P1 V1 ln V2 over V1. Okay, so substitute into your general equation P1 V1 V2 V1. So you got your 100 kPa times 0.4 meter cube ln 0.1 meter cube per 0.1 meter cube per 0.4 meter cube. Okay, so kPa meter cube, so we got work Newton meter. Okay, right, thank you. Sample problem 3.6. Okay, sample problem 3.6. In the cylinder of a large engine, 1.27 kg of carbon dioxide at 527 degrees Celsius and 20 bar expand isothermally to a pressure of 1.4 bar. Determine the final volume of the gas. Alright, so here we are dealing with ideal gas, which is carbon dioxide. So given 3.6. Okay, so your mass is 1.27 kg and your temperature T1 527 degrees Celsius and P1 20 bar. So given P2 is 1.4 bar. Okay, so PV MRT is a for gas, equation for a gas. So if the correlation between initial condition to a final condition, so we got P1 V1 MRT1 is equals to P2 V2 MRT2. So okay, so down, so temperature is also going up, so we got the final equation P1 V1 is P2 V2. But here we don't have volume 1. Okay, so we need the first condition P1 V1 MRT1 to determine what is the volume 1. So volume 1 is MRT1 over P1. Okay, so R, universal gas constant, for carbon dioxide, you can find it on the appendix at the end of your Cheng L books. You can find what is the R value for carbon dioxide. So the mass, you got the mass, you got the R, T1 also you got, V1 also you got. So you got 1.27 times universal gas constant. You need to determine inside the appendix. Okay, the T1 527. So here is in Kelvin. So you need to convert your temperature with Kelvin times temperature, divided by P1. Okay, bar also you need to convert into PA. Okay, so you need to convert bar into a PA lah. So 20 bar equal to PA. Okay, so you solve it, you can get what is the value of V1. Okay, so from this value, substitute into your general equation. So P1 V1, P2 V2. So V2 is P1 V1 over P2. So you got your final volume for V2. Alright. Okay, thank you. Boundary work for adiabatic process. Adiabatic process is one that occurs without transfer or heat or mass between a thermodynamic system and its surroundings. So energy is transferred only as work. So we assume that the surrounding has been insulated, which is no heat being transferred. So here we call it as a adiabatic process. Also, it known as isotropic process, which means that no change in heat. Adiabatic versus isothermal. Isothermal, constant temperature. So isothermal process is one in which the temperature is constant. Heat can be gained or lost in order to maintain a constant pressure. An adiabatic process is one in which there is no heat exchange between the system and its surrounding, and it does not matter whether the temperature of the system is constant or not. For ideal process PV N, for adiabatic process N is equal to K, then your PV K is equal to constant. So substitute into your boundary work. So we got the K minus 1, P1 V1 minus P2 V2 divided by K minus 1. So your K is a specific heat ratio, which is Cp divided by Cv. So property relation of ideal gas from state 1 to state 2. From this equation, PV to the power of K is equals to constant. So we rearrange, you got this value lah, or this equation. Also we can determine the volume. Okay, if you have time, you can prove this relation. Sample problem 3.7. Okay, sample problem 3.7. Air at 20 degrees Celsius in the cylinder of a diesel engine is compressed from an initial pressure of 1 atmosphere and volume of 800 cm3 to a volume of 60 cm3. Assume that the air behave as an ideal gas given K equivalent to 1.4 and that decompression is adiabatic, find the final pressure and temperature of the air. Alright, so here we got adiabatic process condition. So adiabatic is equivalent to isentropic process. So here we are dealing with ideal gas. So 3.7 given the air at T1 is equal to 20 degrees Celsius and P1 1 atmosphere. So we need to convert this into ATM, or if not, you maintain atmosphere. So the final answer, the pressure, is also in ATM units. Okay, and the volume V1 is 800 centimeter cube. So given also V2 is 60 centimeter cube. So K given directly, we assume at ideal gas condition you got 1.4. So from here you got adiabatic process condition. So P1 over P2 is equals to V1 over V2 K. So from here we can determine what is your P2. So if you are using so equals to using atmosphere, so is in ATM value lah. So V1 and V2 you got your value, P1 also you got value. So the condition substitute, you got the value lah. Okay, and T1, the question is to find the final T2. So T1 over T2, you can use either P1 over P2 at K minus 1 over K is also equivalent to V2 over V1 K minus 1. So either one you can use to find your T2. This is degrees Celsius. Okay, all right, thank you. Boundary work for polytropic process. So basically polytropic process is a thermodynamic process that obeys the relation of PV to the power of N equals to a constant. Okay, so basically where P is your pressure, V is your volume, and N is the polytropic index, whereby is any real number, any number, and your C is a constant. So basically when you rearrange the equation, you got similar with isothermal, similar with adiabatic. Okay, but adiabatic have a specific heat ratio K, whereby here we use N. So if let's say the condition your N is equal to your K, say we can use the equation for adiabatic. Sample problem 3.8. Okay, so 3.8, given directly V1 is 0.05 meter cube at P1, T1 is 160 degrees Celsius and P1 is 180 kPa. So the T2, P2, pressure 2 is 90 kPa. T2 is 110 degrees Celsius. So determine the boundary work. Alright. So here, as we have a polytropic condition, so work is P2 V2 P1 V1 1 minus N is equal to M R T2 minus T1 over 1 minus N. As assuming that the property relation of ideal gas from state 1 to state 2 is similar with adiabatic, so we have your N value is equals to K. So we assume that your at K is 1.4. Okay. Alright. So here we can use either this equation or this equation. Okay. So depend on the parameter given from the question. So from this question we have V1, T1, P1. Okay, we have P2 and T2. Okay, either we want to use this equation or this equation, depend, because your R is an argon gas. You can get from tables A1 appendix. We can refer the argon gas. What is the value for universal gas constant? Alright. So here, if you use R for this, also can, should be no problem. Here also you can use. Okay, so here you can determine the volume 2 using the adiabatic condition, which is P2 over P1 is equal to V1 over V2 minus K. So you can get what is your V2 at V2. So either equation you can use. So here I am using this equation. So work is here also, but the problem is mass is not given. So we use this equation lah. So P2 V2, so you got 90 kPa times V2. You need to determine first using this equation, V2. Okay, minus P1 100 kPa times your V1 0.05, okay, divided by 1 minus 1.4. Okay, so you need to determine first V2. So you got your third. Okay, alright, thank you. This is the summary of work. So this formula can be used as a guideline in order to remember more on the formula regarding each process involved and the boundary work involved for each of the process. So this is the diagram. PV and TS diagram for boundary work. Summary of boundary work. Sample problem 3.9. Alright, so sample problem 3.9. Sketch a PV diagram, pressure to volume diagram, showing the following processes in a cycle of piston cylinder device. So process 1 to 2, isobaric work output of 10.5 kilojoule from an initial volume of 0.028 meter cube and pressure 1.4 bar. Process 2 to 3 is isothermal compression. Process 3.1 is a isochoric heat transfer to its original volume of 0.028 meter cube and pressure 1.4 bar. So the question is, calculate the maximum volume in a cycle, B, the isothermal work, and C, the net work. So 3.9. So we have three processes. Okay, process 1, 2, isobaric work is equal to 10.5 kilojoule. Volume V1, initial volume V1 0.028 meter cube and P is 1.4 bar. Okay, given process 2, 3, isothermal and 3.1 is isochoric. Volume 0.028 meter cube and pressure remain constant at the same at 1.4 bar. So from this we know that is a cycle, because from the initial up to the final state condition, so it's come back to its original condition. So it's a cycle process. So drawing the chart. First of all, we know that for point 1 is a PV diagram, pressure to volume. Okay, so process 1 is a isobaric. Isobaric is a constant pressure. So from 1 to 2, okay, so this is your initial value V1, this is your V2, P1. Alright, and then isothermal compression. So isothermal, when it comes to isothermal, there is change in volume and also the pressure. So as it involves isothermal, so basically normally the volume will be reduced. So 3, and then isochoric heat transfer. So isochoric is a constant volume process, so it goes to initial condition. So that is your chart diagram, PV diagram. Okay, for process 1, 2. So is a process given work is given, pressure is given, volume is given. So the total work is P V2 minus V1. So V2 we don't know, V1 we have, pressure also we have, and the total work given directly is 10.5 kilojoule. It's a point. So from this, rearrange the equation so you can get the V2 meter cube. Alright, so we got your V2, we got V2 value. And then section 2.3 is isothermal. So isothermal compression, so indicate here is your we don't know the problem is that we don't know the pressure for P3, P1, P2. Here the P we don't know, so we need at initial condition point 2 we have P, we have V, but here we got V but we don't know P. So if we have a, let's say for example here is a, we're assuming ideal gas, so PV MRT, PV MRT, so 2 2 2 3 3 3 cancel out. So it's a isothermal condition whereby your temperature is constant, T2 T3 is a isothermal is equals, so we got P2 V2 is P3 V3. So P2 V2 we got, P3 we don't know, V3 is the same as V1, because at the end of the day the process number 3 is isochoric and it's come back to its original condition. So the volume is the volume is constant. So from here we can get your P3 bar. Okay, alright. The work for isothermal compression. So work P2 V2 ln V3 over V2. So we got P2 V2 V3 and V2 also we got. So by that we can calculate kilojoule. Okay, alright. So in process 3.1, here the units involved we got, so here you can recheck the units. Is let's say we convert it first to PA, and we got the cube times ln meter cube per meter cube, unitless, so PA times 3 you got joule. Okay, alright. So for process 3.1 is an isochoric. Normally for isochoric, work is 0. So the total work, or we call it as a work net, work 1, 2 plus work 2, 3 plus work 3, 1. So here 10.5 joule plus here your value plus 0. So the total you get kilojoule. Alright. Okay, thank you. Sample problem 3.10. Okay, sample problem 3.10. A fluid at 3.10. A fluid at 4.15 bar is expanded reversibly according to law PV equals to constant to a pressure of 1.15 bar until it has a specific volume of 0.12 meter cube per kg. So it is then cooled reversibly at a constant pressure, then it's cooled at constant volume until the pressure is 0.62 bar and is then allowed to compress reversibly according to law PV to the power of n equals to constant back, we call it as a polytropic, constant back to the initial condition. The work done in the constant pressure is 0.525 kilojoule and the mass of fluid present is 0.22 kilos. Calculate the value of n in the force process polytropic, the net work of the cycle, and sketch the cycle on a PV diagram. Okay. So here we got 4 processes. So we have a fluid. So for fluid we got 2 types. Fluid we have solid and fluid. So fluid we got liquid and gas. Okay, so here if we use liquid, so we must know what is the character of the liquid. Either is a water, either is a mercury or refrigerant something, but here in the question it doesn't state at what types of liquid being used. So we assume in this example we assume it involves gas, so we can use PV MRT. Okay, alright, so section 1, 2 we have isothermal as given PV is a constant, so is a isothermal condition. Okay, so given P1 4.15 bar, P2 1.15 bar, V2 0.12 meter cube per kg. Section 2.3 is cool reversibly at constant pressure. So constant pressure we call it as a isobaric. So constant pressure isobaric. So P2 we have, volume 2 we have also. Alright. So in section 3, 4, then is a cool at constant volume is a isochoric. And lastly, it's allowed to compress reversibly according to a law PV to the power of n equal to constant. So 4 to 1, here constant volume until the pressure is P3 0.62 bar. So isochoric constant volume. So polytropic 4.1 is a polytropic, as it PV n is equal to constant. Okay, so how does it looks? PV. So firstly is a isothermal. So isothermal normally is a something like that, to the left and it's upwards, but here is expanded reversibly, so it will go backward to the right to lower condition, and then constant pressure reversibly constant pressure. If you have normal isobaric, we have to the left. So here is reversibly, we have to the right. And then isochoric constant volume. So basically isochoric, the pressure will be lower from the initial pressure. So constant volume. If in this case the example doesn't state whether it's a reversible or not, so we assume it's a normal condition, so it goes back. So this is your 1, this is your 2, this is your 3, this is your 4, and lastly polytropic. Polytropic is at reversibly. Normally it goes something like that, so it goes reverse. Okay, so polytropic is somewhere from your left to the right, but it's a reversible, so we got from right to the left. Okay, so that is your diagram. Okay, so we go section by section. So 1, 2, isothermal. So as we don't know the initial volume, because given here is the final volume at 0.12 meter cube per kg. So basically the initial volume we need to determine first before we can calculate the work done. So isothermal condition, so which means that temperature is remain the same, P1 V1 MRT1, P2 V2 MRT2. So take out, and T1 is equal to T2 isothermal. So left out P1 V1 and also P2 V2. So V1, so as pressure, initial pressure given, volume 1 you need to calculate, final pressure also given 1.5, P2 is 1.15 bar, P1 is 4.15 bar, V2 is 0.12 meter cube per kg. Okay, so we can substitute into a general equation. We can get your V1 meter cube per kg. Okay, so if you want to get in VB meter cube, V1, so the fluid meter cube per kg times 0.22 kg. So here 0.22, the mass is given in the question. So take out, you got your final volume. Okay, then we can calculate the work. P1 V1, this is from the notes, V2 over V1. So given all, then substitute into your general equation. So the all value has been given, so you can calculate what is your kilojoule value. Let's say we got here A, so you can calculate what is the A value. Okay, section 2.3 is a isobaric. So all has been given, so your pressure also given, isobaric pressure is given, and okay, so here P3 isobaric pressure given, P2 and P3 same pressure. Okay, so we got V2, we don't know V3, P2 is same with P3. So determine first the value of V3. As given in the question, the work isobaric is being given directly in the question at 0.525 kilojoule, and therefore in order to determine the value of volume 3, so work P V3 minus V2. Okay, so P is constant at 1.15 bar, V2 we got the value V2, so V3 we got your answers, meter cube. Okay, alright, so we move on into the section 3.4. S is a isochoric. Your work is 0. So section 4.1. Alright, so here V3 we got, so V3 and V4 is same. It's a isochoric, okay, and then is polytropically, okay. So the question is to determine what is the value of n polytropic process, PV to the power of n. So we can determine by using the n. So all of the value, so P1 we got the initial condition 4.15. So at this we got 1.15 bar. So the loss is 0.62 bar. So all of the pressure line has been determined. So we can determine P4 is 0.62. P1 is 4.15 bar. So initial volume has been determined, and volume 4 is same with volume 3. So here just solve it. Ln P4 P1 is equal to, and ln V1 over V4 and ln P4 over P1 ln V1 over V4. So we got the answers. So the work done, P1 V1 P4 V4 divided by 1 minus n. So n here substitute into a general equation. So P1 also has been determined, V1 also, P4 V4. So you can get direct answer. Okay, thank you.